Let us find counterexample for the following universal statements. For every real value, the real value is more than equals to reciprocal. Is this true? We can basically find an example that makes this statement to be a wrong statement, and we call it a counterexample. For example, if you said x equals to a half, well, a half is not more than equals to 1 divided by a half or 2. So this one is a counterexample for you. Next universal statement says, hey, for every integer, a minus a, 1 divided by a is not an integer. We can easily find counterexamples here. Counterexamples are examples that make this statement to be a false statement. Set a to be 1, so obviously 1 minus 1 divided by 1 is 0, which is indeed an integer. You can find many, many more examples here. Another counterexample for you is -1. If I plug in -1 here, -1 minus 1 divided by -1 gives you 2, which is indeed an integer. Next universal statement says, for every positive integers like m and n, the multiplication between m and n is more than equals to the summation of m and n. You can find counterexamples, not just one, many. One of them here is set m to be 1, n to be 1. So obviously, the multiplication between m and n is 1, but if you add them together, it becomes 2. So obviously, 1 is not more than 2. So we found a counterexample here. Next universal statement says, for any real number like x and y, the square root of x plus y can be written as square root of x plus square root of y. Well, again, here we have many, many counterexamples. For example, set x to be 1, y to be 1. The square root of 1 plus 1 is square root of 2. Square root of 1 plus square root of 1 gives you 2. And left-hand side, right-hand side are not equal to each other. So we found a counterexample here. Let R be the domain of the predicate with variable x. Which of the following are true and which ones are false? Give counterexamples for the statements that are false. So A says x is more than 2, so we can conclude that x is more than 1. This is a true statement. Any real number that is greater than 2 is indeed greater than 1. So this is a true statement. B says if x is more than 2, then you can conclude that x squared is more than 4. So this statement translates into, for every real number like x, if x is more than 2 or greater than 2, then x squared is more than 4. Well, obviously, this is a true statement. Part C says x squared is more than 4, so you can conclude that x is more than 2. This statement is a false statement. Consider -3. -3 to power 2 is 9, which is more than 4, but -3 is not more than 2. D, it says x squared is more than 4 if and only if absolute value of x is more than 2. This statement translates as, for every real number like x, if the square of the number is more than 4, then you can conclude that the absolute value of x is more than 2, or if the absolute value of x is more than 2, you can conclude that the square of that number is more than 4. This is a true statement. We are going back to algebra. X squared is more than 4. It means that x is more than 2, or x is less than -2, or translates into the absolute value of x to be more than 2. For a universal conditional statement, for every x, if p of x, then q of x is basically a universal conditional statement. So when it comes to conditional statements, this is a universal statement. It's not an existential statement. Let us review the truth table for P then Q. On the very first row, we have P, Q, and the statement P then Q. If P, then Q. If P is true, Q is true, P then Q is true. P true, Q false, then you get a false statement. If P is false, or the hypothesis is false, the conclusion is true, then the statement itself is true. And if the hypothesis is false, the conclusion is false, you say that, hey, the conditional statement is true. Let's write the universal conditional statement informally. For example, consider the following statement. For every real number, if x is more than 2, then x squared is more than 4. Basically, we can write it this way. If a real number is greater than 2, then its square is greater than 4. So if is a conditional statement, a real number. So here, for every real number, if x is more than 2, then you can conclude that its square is more than 4. Or whenever a real number is greater than 2, its square is greater than 4. Or you can write it this way as well. The square of any real number greater than 2 is greater than 4. Or you can write it this way. The squares of all real numbers greater than 2 are greater than 4. Suppose P and Q are predicates, and suppose that they have a common domain for variable x, which is d. The notation Px then Qx means that every element in the truth set of Px lands in the truth set of Qx. Or for every x, Px implies Qx. The notation Px, if and only if Qx, means that P and Q are identical in truth sets. Or equivalently, for every x in their common domain, Px, if and only if Qx. Let Qn be the following predicate. It says n is a factor of 8. Rn be n is a factor of 4, and S of n with the following predicate. N is less than 5, and at the same time, n is not 3. Suppose the domain of n is positive integers. Now, the truth set of Qn is the set including 1, 2, 4, and 8. These are the only numbers that are factor of 8 and are positive integers. By similar reasoning, the truth set of Rn, which n is a factor of 4, are 1, 2, and 4. The only factors of 4 that are positive are 1, 2, and 4. So, it's true that every element in the truth set of Rn lands in the truth set of Qn. Equivalently, we can write for every n in positive integer, Rn implies Qn. Or basically, Rn implies Qn. Or equivalently, n is a factor of 4, then you can conclude that n is a factor of 8. We can show that these statements are also equivalent because Sn is the set of all values, real, the z values, which are basically your integers. Sn, we all n values, that n is less than 5, and n is not 3. So basically 1, 2, and 4. So you can say, hey, these two statements are equivalent to each other. And since n implies Qn, we can conclude that Sn implies Qn as well. What's the negation of a universal statement? The negation of a statement of the form, for every x in domain D, Qx is basically an existential statement. It can be written as for every there is x in D such that the negation of Qx. So the negation of for all is there exists. The negation of a universal quantifier is existential quantifier. You only need to negate the predicate itself to get the negation as well. Symbolically, the negation of universal quantifier, or this case, universal statement, is an existential statement. So please note that the negation of universal quantifier is existential quantifier, and you just need to negate the predicate, which, as you can see here, not QX. With the same argument, the negation of existential statement is going to be a universal statement. So if you have an existential statement, like there is X in domain D such that QX, its negation is going to be for all X in D, not QX. So again, please note that the negation of existential quantifier is universal quantifier. Symbolically, we write it this way: the negation of existential quantifier, which is universal quantifier, and you just need to negate the predicate itself. So I expect you to ask, what if we have a universal conditional statement? What is the negation of a universal conditional statement? When it comes to the negation of a universal conditional statement, remember that you have a universal quantifier. If Px, then Qx. It can be written as there exists an X such that Px and not Qx. Consider a statement of the following form. For every X in domain D, if Px, then Qx. Recall that we defined the contrapositive to be not Q, then not P. But since you have a universal statement when it comes to conditional, you're going to keep that as it is. We're not finding the negation. We're just rewriting the contrapositive using a quantifier. For a converse, it's the same. It's a universal quantifier that you're going to use here. You have a universal statement for every X in D, Qx, then P of X. And finally, as you remember, when you have an inverse, the inverse of Px, then Qx is not Px, then not Qx. And again, we're using a universal quantifier to represent each one of these. None of these are existential statements. All of these are universal statements. Also remember that at the beginning chapter, we said the negation of P, then Q, is equivalent to P and not Q. So this is why when you're negating an universal conditional statement, it becomes the format of P and not Q, and then you're going to negate this statement. So when you're negating the universal statement, you're going to get an existential statement back, and you're going to copy down Px and the keyword here and not Qx. For example, let's take a look at a few examples here. We want to write the negation for each statement here. Each one of them is a conditional statement. For every real number x, if x is more than 3, then x squared is more than 9. The negation is, so the negation of universal becomes existential. You're going to copy the hypothesis as it is. You're going to convert then into and. So this is the important part. And then x squared more than 9 becomes x squared less than equals to 9, which is basically the negation of Q, or negation of the conclusion, which is x squared more than 9, which becomes x squared less than equals to 9. Well, another example for you. For any computer programs like P, if P compiles without error messages, then we can conclude that P is correct. So first of all, let us find this negation. The negation of universal becomes existential. So you have an existential quantifier. There exists a computer program like P such that you're going to copy the hypothesis. P compiles without an error, and which now you can just write it as but P is not correct. So the negation of P is correct. It's going to be P is not correct. As easy as that. So when you're negating a conditional statement, you copy down the hypothesis and the negation of the conclusion. Let's take a look at another example for you here. For example, for every real number x, if x squared is more than 1 or is equal to 1, then you can conclude that x is positive. The existential statement that you get from negating it says there is a real number like x such that copy down the hypothesis as it is, convert then into and negate x positive. When x is not positive, x is not more than 0, x is less than or equal to 0. Or other words, there is a real number like x such